The next subject we're going to talk about on impulse and momentum is the angular impulse and angular momentum. And we're discussing this issue again for particles. You will see that we're going to discuss these issues in also bodies, rigid bodies, and it will be somewhat different than our formulations. But investigation of the particles gives us some of the main ideas, some of the fundamentals on these concepts, so it's very important. What we have on this graph is a particle, and the particle has its linear momentum mv, and that's going to be changing throughout the path. And the linear momentum at any point is defined as g equals to mv. This is what we know from our previous part of this lecture. Now we're going to define the angular momentum. The moment of linear momentum about an arbitrary point O is called the angular momentum of P. P is our particle about O, and it is identified by H subscript O, and then you should be aware that there's a vector sign on top of it, so this is another vector we are talking about. The angular momentum is also a vector as the linear momentum. But I will have some good news about you. Since we are working on planes, we can get away with just the scalar version of this formulation. Now, that being said, O could be any point. So if you take a look at this figure on the left, there's an O point, and then with this we define the angular momentum HO. This is a vector. Okay, HO with respect to this vector multiplication, the cross product operation, R cross product MV. But this O point can be any other point as well, so we can discuss about a point A here. Okay, and then we can find the angular momentum of P with respect to A. Obviously, it's going to be different than the angular momentum that you're going to calculate about O. So this is up to you. This is your selection of the point that you would use to calculate the angular momentum. So that's why you need to have this subscript to define for which point you're calculating this angular momentum. So angular momentum is calculated by this cross product operation, R cross product the linear momentum. Now if you take a look at this definition of the theta angle with respect to this line of R, is this vector R, it forms a plane. This R vector and then the MV vector, they form a plane. And as we are taking the cross product of these two vectors, the cross product, the result of the cross product, the vector is the result of the cross product, and that vector should be in the normal direction or to this plane that is formed by R vector and MV vector. That's why we have this plane shown here, and then there's this vector of the angular momentum perpendicular to this plane. Now for three-dimensional cases, you need to work with the idea of this vectors, but then for the two-dimensional cases, we can get away with a single equation, a single scalar equation, and this is kind of like the description of that. So if we have this point O right here, and then we are trying to find out the angular momentum about point O of particle P, and then the particle P has this MV, and this plane that we are working here is the same plane that we have here. This is the A plane. Okay. So on that A plane, if we take a look at that plane from the top, this is what we're going to see. This is angle theta, and the cross product will result in MV R sine theta. And in this way, either you say this is R sine theta times this perpendicular, so we have this perpendicular relationship here, so that we are able to find the cross product, or you can find the component of MV right over here, and let me just show you the theta angle. Theta angle is right over here, so this is MV times sine theta. So this part is mv sine theta. To see this writing, but anyways, so you get the same result, either r times mv sine theta or r sine theta times mv. It's going to result in the same angular momentum calculation. If you need to work with the notion of these vectors, this is the cross product operation. This x, y, and z are the components of the r vector in x, y, and z. And then this is something that you should have seen in your math courses. This is the way of the vector calculation. But like I said, we're working on planes, so this is good enough. This part, a scalar equation based on this, is good enough. In other words, what we are defining here is a d distance that is going to be perpendicular to the mv. So you can get away with just saying m times v times d, and then define this d to be equal to r sine theta. Now, what we have learned in the previous lecture on lecture 6 about linear impulse and momentum is that we have this Newton's equations, the modified version of it as v dot. Now, if we multiply both parts of this equation, cross multiply with r, then what we have on the left hand side is the moment about O. The moment is due to the net forces acting on this particle, or the resultant force on the particle, or the summation of all the forces acting on the particle. They are all the same thing. So the net forces acting on the particle, it forms a moment about point O, and you can calculate that by R cross product, the summation of all forces, and it equals to this part where it is saying that R cross product mv dot. As a matter of fact, we just defined the angular momentum as R cross product mv. Now, if we take the derivative of this equation with respect to time, so ho dot, then we get two parts to that. We get r dot cross product mv plus r cross product mv dot. Now, if r stays constant, that means O is a fixed point. It has no relative motion. In that sense, this part disappears because O point becomes a fixed point, and r dot is actually the velocity that you're going to measure with respect to this fixed point, and the velocity measured with respect to a fixed point is actually the absolute velocity, and the velocity vector we have over here is also absolute velocity. So vector cross product by itself is equal to a zero vector, so this part cancels out, and at the end what we get is r cross product mv dot, which is the same thing that we had over here on the right hand side of the equation. So now we can say as the summation of moments acting on a particle calculated about point O is equal to the time rate of change of the angular momentum. This h dot O is the time rate of change of the angular momentum calculated about point O. And if we do the integration with respect to time, like we did for the linear impulse and momentum equations, at the end what we get is the impulse of the moment in the time interval from t1 to t2 results in the change of the angular momentum calculated about the same point at different times, time 2 and time 1. And here we see the difference of the angular momentum. These are calculated at different times.